Welcome to Get Well HS. Here we have an excellent question which is untold on variable friction coefficient. So here and it is also under collision. So collision and friction both combined question. Let's go through the question. Two blocks A and B moving on a frictionless surface initially collides and slides on to a rough surface which has variable friction coefficient over with some velocity combined together and comes to rest after traveling distance t. So there are two blocks, one of mass 3m and other of mass m. So we can easily say this is having more momentum, this is having less momentum. So when more momentum collides with less momentum, we can just know if it is an elastic collision, we can just know the direction of the collision. So the direction of the moment of blocks after collision. So this will stick to, the small mass will stick to capital mass and this will move in this direction, right side. So whenever they just collided, they were onto a rough plane. So whenever they are just collided, they were onto a rough plane at x is equal to 0. And on the rough plane with variable friction coefficient mu k of x, since they are under movement, we will be having kinetic friction. So kinetic friction coefficient is equal to b into x square. On the rough plane it is moving, and it since rough plane there will be dissipating a form of energy due to kinetic friction, so it comes to rest at x is equal to d. Okay, find the final velocity of the blocks after just elastic collision. So we need to calculate the final velocity of the blocks. Also comment on conservation of momentum and energy under friction. Also like how we can take conservation of momentum and conservation of energy under friction and collision, how we will be taking that. So let us solve the question. Just before solving the question, we need to note a few points. That here initially it is having elastic collision, right? So in elastic collision and on a smooth plane, there is no external force acting on the two blocks, so we can just simply apply conservation of momentum. Since there is no external force, we can just simply apply conservation of momentum. So we'll do that. We'll apply conservation of momentum here initially. Conservation of momentum. Thing to note is, if there is an external force, conservation of momentum cannot be applied, but conservation of energy can apply. That we will conclude at last. And so just finish with this conservation of momentum. P final along this direction minus that is equal to P initial, just to represent the vectorial form of momentum. So P final, what is a P final we are having? P final is just both the blocks will collide and they start moving with some velocity called Vf, and we need to calculate find the velocity of the blocks just after collision. So we need to calculate that Vf value. So for that, 4m into Vf is nothing but equal to, initially they are having some momentum. That momentum is 3m into V naught along right side directions. 3m is moving along right, so it is positive, minus m into V naught. So from that we will get Vf is equal to V naught upon 2. So the final velocity is half of the initial velocity of the blocks. But we need to also to calculate what is the initial value, then we will get the final value. For that we will use, since it enters into rough plane just after this collision, when it starts with velocity Vf, it enters the rough plane. On the rough plane we will apply work energy principle. So we will do it in another page. So we will apply work energy principle on rough plane. Work energy on rough plane. Right, we'll apply work energy on the rough plane. W is equal to, so work energy is nothing but the work whatever being done by the block on movement on a rough plane is equal to the change in kinetic energy of the block. So work done is nothing but change in kinetic energy of the blocks. So first we will calculate work done. See, always work done is integral f dot ds. This is the representation of work done. But here, since it is in one-dimensional case, it is always a movement along a linear direction. Let the linear direction be x. We can write it as fx dot dx integral. and here the limits are like it starts on the rough plane at x is equal to 0 and ends its movement at x is equal to d. Due to friction there will be dissipation of energy in the form of work. So here the work is done by the frictional force. That frictional force is nothing but Fk. And also since we have taken direction along x, but the frictional force is opposite to the direction of x, so it is always negative. So Fk into dx from x is equal to 0 to x is equal to d, and we know Fk is nothing but mu k into dx, so minus integral x is equal to 0 to x is equal to d mu k into n is nothing but mg, we will write it later, into dx. And in the question mu k is given as mu k of x, so mu k is varying here with the distance, so as the distance increases the mu k also increases. So w is equal to minus integral bx square into mg into dx from x is equal to 0 to x is equal to d. Actually here it is 4 mg, so all the two blocks were combinedly moving together, so it is 4 mg. Right. Once we do the integration, we will get the value like minus 4 b mg d cube upon 3. This is the work done, and that must be equal to the delta ke, and delta ke is always k final minus k initial. We know k finally the block will be to rest, so final kinetic energy will be 0. We'll have only initial kinetic energy, that is equal to minus of half into just the initial kinetic energy, mean when the block started x is equal to 0. At x is equal to 0, the 4m mass of the block will start moving with velocity vf, so vf square, right? And from that we'll get this as half 4m minus 2m vf square, and this should be equal to minus 4b mg d cube upon 3. Once we do the calculation here, the vf value will be, the 2 and 4 will be cancelled 2 times, so it will be 2b g d cube upon 3 under root. This is the final velocity of the blocks just after collision, and this is our answer, right? So here the question was finished, and also here they asked to comment on the conservation of momentum and energy under collision. See, when it is an elastic collision, we can say that complete momentum will be conserved and also complete energy will be conserved. Here even it is an elastic collision, but there is an external force acting just after the collision. So after the collision, in the moment there is an external force being acted. So here till there is no external force, conservation of momentum can be applied. So that is why here on the smooth plane we applied conservation of momentum. No issue there, we can apply. But if it is on a rough plane, here even if here it is having some friction, we cannot apply conservation of momentum here. Okay, and also once it enters the rough plane, here we can't apply conservation of momentum, but we can apply conservation of energy, because see, when they are starting with some kinetic energy and they are ending with zero velocity, means zero kinetic energy. So where does this complete kinetic energy go? It goes in the form of doing work against the friction. So this block has to move against the friction. So this kinetic energy is being used to do work against the kinetic friction. So that's why we applied work done, and here for force term we have taken friction, and here since it is under moment, the friction will be kinetic friction, and that is given as mu k, and here mu k is variable as bx square, right? Thanks for watching.